Hello everyone, I hope you're all doing well. We're going to be looking at particle kinetics in this brief concept talk. Okay, so kinetics. What do we do in kinetics? Okay, we look at the forces acting on the particles and we try to understand how they influence the kinematics of the particle or the motion of the particle. Okay, so we look at forces acting on the particle. Because we are doing particle kinetics. If you're doing a rigid body kinetics, then you'll be looking at the forces acting on the rigid body and see and understand how the motion or the kinematics are influenced by the forces. Alright, so now we are coming to real dynamics, where we start making use of the ideas that we have seen earlier when we did particle kinematics, and we'll follow the same procedure where when we look at rigid bodies as well. Alright, so what I'm going to do is I'm not going to go over like the foundational things and so on in kinematics, which we have already gone through. Okay, so I'm just going to outline a basic procedure for solving problems in particle kinetics. Okay, so basic procedure for solving problems in particle kinetics. All right, and this basic procedure employs like a few steps. Some of these steps we already have an idea of from either statics or from particle kinematics. Okay, so the first thing and the most important thing is choose a suitable coordinate frame based on the nature of the problem. Okay, so choose a suitable coordinate frame based on the nature of the particle as motion. Okay, based on the nature of the problem of the particle motion or the problem. Okay, and here you have several choices. What are your choices? You have Cartesian system, where your unit vectors are I and J. Okay, then you typically have your normal tangential system, where your unit vectors are ET and En. Let me write my T properly, otherwise that looks like a theta. All right, and then we have a radial transverse coordinate system or a polar coordinate system, where your unit vectors are E theta and ER. Okay, so this is the best thing to do in any problem, is to choose a suitable coordinate frame. Okay, this is where the problems are either made or broken, and the most important step in pretty much all problems. All right, the second step is to draw a free body diagram of the particle. Okay, so draw a free body diagram, or the FBD of the particle. Okay, on the free body diagram, this is something that you have encountered in statics. Okay, so you draw, so on the FBD, okay, you draw all the external forces and you draw all the external moments. If there are any on a particle, there is going to be none. Okay, external moments if you have a rigid body. The procedure I'm outlining is basically going to be similar for a rigid body as well. Okay, and then you also draw out the support reactions and so on. So constraints or supports. Okay, for example, it's a ball held on a string, right? Then what is the constraint? The constraint is going to be the tension of the string. Okay, so something like that. Okay, this is what you draw on the free body diagram, and it's very, very important that one draws very clean free body diagrams, because the cleanliness, or in a sense, you see what I'm saying, the cleanliness of a free body diagram tells us how cluttered or uncluttered our thinking is. Okay, that's the second step. The third step comes where there's a slight change from your statics. We draw what is called as the kinetic diagram of the particle. Okay, so draw the kinetic diagram or in a sense I'm going to call this as the KD of the particle. Okay, and here is what you do in the kinetic diagram typically. So on the kinetic diagram, depending on the coordinate system that you have chosen, you'll be marking the mass times acceleration quantity. Okay, so depending on coordinate system chosen, we shall mark the mass times acceleration quantity on the kinetic diagram. Okay, kinetic diagram is also sometimes called as the mass acceleration diagram. Okay, so the kinetic diagram is also called as the mass acceleration diagram or MAD. People have gone mad at drawing this, typically students. All right, but I'm going to help you get there. All right, so there are some basic examples of typically what you do. Okay, so let me look at very brief examples of what we do. Okay, so just a digression. So common examples of kinetic diagrams. Common or generic example. Okay, so typically I would let's say that I have a particle here. Okay, on the free body diagram, what would I do? I would be drawing the forces that are acting on the particle. Okay, so maybe there are some forces that are acting on the particle. Maybe the particle is held by some kind of a string or something. Okay, so maybe these are the forces acting on the particle. So this could be the tension of the string. Then perhaps these are some external forces F1, these are some forces F2, and so on. Okay, and this is going to be the free body diagram. This is the FBD. Okay, now the kinetic diagram, typically what you do is this. I draw the same particle, of course. Okay, and if you have chosen to solve this problem in the Cartesian coordinate frame, then here is typically what you do. Okay, you say, okay, hey, I've done the Cartesian coordinate frame, so I set up the unit vectors of the Cartesian coordinate frame. So this is going to be the I direction, and let's say this is the J direction. Okay, so I'm going to draw the unit vectors in a minute. Okay, so this is the I direction, and let's say this is the J direction. Then on the kinetic diagram, you'll be drawing two forces which I already drawn here. Then you'll be calling that as mass times acceleration in the x direction, mass times acceleration in the y direction. Okay, And typically mass times acceleration in the x direction, I would write it as m times x double dot, and this would be m times y double dot. Okay, so this would be the kinetic diagram in the Cartesian system. Okay, so that could be one situation, or I could have another situation where I can draw the kinetic diagram. So I'm going to just put a divider here, okay, where I'm drawing the kinetic diagram. Well, did not come out too straight, and that did not come out too straight either. There is some magical events happening here, folks. Okay, so this could be the kinetic diagram in the Cartesian system. Okay, or I could have the kinetic diagram in the normal tangential coordinate frame. Okay, so here is what I would do. First thing is I would draw the particle. Okay, then I would set up the normal tangential directions, depending on how the particle is traveling, of course. Okay, so maybe the particle is traveling this way, along a curve. I don't know, I'm just seeing. Okay, these are the directions and so on. So maybe let me shorten the length of my arrows here. Okay, so let's say that this is a small one here. Okay, and then this is a small one here. So these are my directions, E, T and En. Okay, these are my normal and tangential directions, and then I draw along those directions. I have to draw a mass times acceleration. Okay, so this is going to be mass times acceleration in the tangential direction, and likewise I'm going to have a mass times acceleration in the normal direction. Typically normal acceleration we know is v square divided by rho, and tangential acceleration we know is m times v dot. Okay, so this is going to be the kinetic diagram in the normal tangential system. Okay, all right, so that's one more case study. Okay, maybe let me scoot these things a little below so that they're not that crowded on there. All right, or I could also have the following situation. Okay, I'm going to extend this line here. I could also have the following situation where maybe a better choice for solving this problem would have been the polar coordinate frame. So if that was indeed the case, I would have the particle as the following. So maybe the particle is sitting this way. Okay, so perhaps the unit vectors in the radial and transverse direction are this way. Okay, so let's say that this is some ER, and then let me say that, okay, perhaps this is the direction of E theta. Okay, so this is E theta, and then I would mark on the kinetic diagram, okay, the mass times acceleration in the radial direction, which, as you know from kinematics, is m times r double dot minus r theta dot square. Okay, and then on this direction where I have the transverse direction, I would mark the mass times acceleration in the transverse direction, which is m times 2 r dot theta dot or theta double dot. Okay, and this would be the kinetic diagram in the radial transverse system. Okay, I hope this makes sense. All I'm doing is I'm drawing the same particle, but instead of marking the forces, I'm marking the mass times the acceleration of the particle. Okay, so this could be the situation, and for each of these cases, depending on what coordinate frame that I've chosen, the free body diagram will be drawn. Okay, based on that particular coordinate frame. Okay, in this situation, maybe my coordinate frame chosen was, for the free body diagram, the I and the J direction, as I have taken on here, right? Or perhaps I could have a situation where let me maybe do this before I destroy my figure here. I'm going to copy this figure and paste it a few times. Okay, I'm going to copy that and paste that here in the second situation, and paste that here in the third situation as well. Okay, so this is situation number 1, right, where I have the Cartesian frame. This is the second situation, and this is the third situation. Then what I want to do is I want to very carefully draw the same unit vectors on the free body diagram as well, just to say that okay, hey, I'm looking at this from the perspective of the Cartesian coordinate frame, or maybe I'm looking at this from the perspective of the normal tangential coordinate frame. Okay, so these will be the same unit vectors drawn in the same direction. So this is going to be En, this is going to be Et. Okay, and this is of course the free body diagram of the particle. Okay, this is the free body diagram, and likewise, if I come here, I will also say okay, hey, this is going to be my radial and transverse direction, and I will be following the same direction that I have marked on the kinetic diagram. Okay, and this is the fundamental or the foundational part of what we are doing. And let me just make sure that we have all of these separated out. Okay, so I'm just going to ensure that these are all different things. I just came across this drawing dotted lines and notability, and I've been going crazy since then. Okay, and one more thing. Okay, so that's the end of it. So as I said, basic procedure is the following. I'm not done, but I'm just recapping what I've done so far. I start off with a suitable coordinate frame. Different choices. What is the choice? It depends on the problem. If the particle is traveling in a straight line path, or it is just performing vertical up and down motion, then obviously Cartesian system is a good choice. But if a particle is traveling on a curvilinear path, then you can have either normal tangential or the polar coordinate frame. Okay, so these are path dependent. Okay, so these are path dependent coordinate frames. Okay, this is a path independent. Okay, as you know from basic kinematics. Then you draw the free body diagram where you mark the forces and the moments and the constraints and so on. Okay, constraints meaning your tension of a cable, tension or normal force, etc. These are typically the constraints, okay, or the supports. And then you draw the kinetic diagram. Very important, how to draw the kinetic diagram is, all you do is just say mass times acceleration. Okay, depending on the coordinate frame. If it's a Cartesian frame, it's mx double dot or my double dot. If it's normal tangential, it's mv dot and mv squared by rho. And if it is a polar coordinate frame, then you have these two quantities here, the radial acceleration and the transverse acceleration components. Make sure that the same coordinate frame is utilized in the free body diagram as well. Okay, then once you do everything, I was on step D, so I'm going to go to step E. So once everything is ready, okay, that is once we have drawn the free body and the kinetic diagram, FBD and KD are drawn, okay, then what do? You make use of Newton's law. Okay, according to Newton's law, force is mass times acceleration. Okay, or here is what you do. Typically in a Cartesian coordinate frame, you would say that okay, sum of all the forces in the x direction is equal to mass times acceleration in the x direction. Okay, or we would say okay, sum of all the forces in the y direction is equal to mass times acceleration in the y direction. Okay, so this would be the Cartesian system. Okay, then let me squeeze in a couple more here. I'm going to have sum of all the forces in the tangential direction. I could say is mass times acceleration in the tangential direction. Sum of all the forces in the normal direction is mass times acceleration in the normal direction, depending on which coordinate frame you've chosen. If this is normal tangential system, And then you'd have the polar coordinates as well, right? So this would be sum of all the forces in the radial direction is mass times acceleration in the radial direction. Sum of all the forces in the transverse direction is mass times the acceleration vector in the transverse direction. This is in polar coordinates. This step is the same as the following. Okay, so the above step is the same as the following. Sum of all the forces in the free body diagram being equal to sum of all the forces in the kinetic diagram. Okay, this is Newton's law. And this is why we are drawing the kinetic diagram. Okay, this is the reason for drawing the kinetic diagram. So essentially what I have written up there is saying, okay, here are the forces in the free body diagram, mass times acceleration. What is mass times acceleration? It's a quantity I'm drawing in the kinetic diagram. So all I'm doing is I'm setting the forces on the free body diagram equal to the forces in the kinetic diagram. Okay, and this is the reason why we are drawing the kinetic diagram. Okay, and you will see that all these terms, mass times acceleration here, mass times acceleration, they're all just the terms or the forces in the kinetic diagram. Okay, mass times acceleration is a force, right? So in a sense, a kinetic diagram is also a free body diagram of a sort. Okay, and once I'm done with all of these, I still have to make use of, so this is once when everything is ready. Okay, so essentially you're drawing the free body and the kinetic diagram, and the fundamental step of the problem where you have, well, that line kind of vanished. I wanted to put a double line. All right, there you are. The fundamental step is where you're setting these two equal to each other. Okay, then once in a while, we will encounter force laws, okay, which will be useful for us. Okay, so I'm going to call that as point F. So sometimes, so some problems require the use of force laws. There are only two that are of interest to me here. One is the spring force law, okay, or the spring law, where the force on a spring is proportional to the displacement of the spring. Okay, so delta S, where this is the spring force. So I guess this is typically for a spring. I thought so. That is not how it is looking like. All right, and so here I say, okay, this is the force on this spring. The K is the stiffness of the spring, and the deflection of the spring in this situation is marked as delta S. Okay, so here this is the spring force. Okay, K is the stiffness of the spring. Let me mark that properly. Okay, so that's the spring stiffness, and delta S, which we have here, and I'm going to mark that this way. Okay, this is the spring displacement. From some equilibrium position. Okay, so this is the spring law that we typically encounter. You've seen this kind of ideas in basic physics, I'm pretty sure. Then something that you've encountered probably in statics a whole lot and made your life miserable is the Coulomb law of friction. Very, very important to understand how this works, and we're going to see that through problems. Okay, so the Coulomb law of friction. Okay, I'm just going to state it and leave it at that, so that we'll come back and look at the problems as such when we are talking about this. Coulomb's law of friction is the following. Okay, so first situation. So if F mu on the particle is less than or equal to mu s times n, okay, where mu s times n is the static friction force, or the maximum static friction force, I'm sorry, is the maximum static friction force, and typically I call this as F mu max as well, so I can typically call that as F mu max. Okay, let me write my max properly. Then it means that there is no motion. That is, you're doing statics, which is fantastic news because we used to love statics, right? So this is the maximum static friction force. Okay, and let me make this a straight line. So this is F mu max. This is according to Coulomb's law. And then you come to the situation where, okay, so if you find out, okay, if F mu on the particle is greater than F mu max, or this is the way I wrote F mu max, then this violates the law, which implies that then F mu particle has to be equal to mu k times n, okay, and there is motion taking place. If it violates the law, then there is motion taking place, okay. So if that is the case, then motion takes place. Okay, and in these situations, as you know, mu s is the coefficient of static friction, and mu k, which is typically less than mu s, is the coefficient of kinetic friction. In my view of dynamics, I don't see a huge difference between the coefficient of static and kinetic friction. So typically for me, I would equate them to be the same value, in a sense. But that is just my philosophy, so I don't want to impound that upon you. But this is the basic idea. If this is the case, in the first situation, if F mu on the particle is less than or equal to F mu max, then there is no motion. If F mu of the particle is greater than F mu max, then it violates the law of Coulomb's friction law, and as a result, you're going to have motion of the particle. All right. So this is the last step in the process of solving a problem. Some problems will require it, some problems may not require it. Probably problems that we're going to solve, all of them are going to be requiring it. Okay, and always keep note of the fact that you are going to have something from kinematics that's going to be of use here. Okay, so maybe I'll just sneak that statement in somewhere here. Okay, so the kinetic diagram, this is typically the situation where kinematics plays the major role. Okay, so in this situation, so kinematics informs us here on what to draw on the kinetic diagram. Okay, all right, so this is the setup essentially, and all we have to do now is start solving some problems and get used to these ideas. All right, I hope you're all staying safe. Take care of yourselves. I'll see you in a problem. Bye bye.